6544 on Thursday, April 3rd, 2014.
Good afternoon, everybody. Let's continue our discussion from last time. We started talking about switched power amplifiers, switching power amplifiers. And again, as I told you last time, the basic concept of the switching power amplifiers is what? Is having a what? Creating a square wave, creating a square wave at the what? At the drain of your transistor, rather than a what? A sine wave. Why? Because if you create a square wave and you expand it in a Fourier series expansion, you will see that the fundamental will go higher than the what? Than the peak value of the square wave. It will go a little bit higher. Clear? It's the ratio of what? Of 4 over what? Over pi. 4 over pi, which is what? A little bit higher than what? Clear? 4 over 3 is higher than 1. Now, first of all, we looked into class D. I did not bring the notes from last time, but we went through it, class D. Now, remember what I said about switching amplifiers. In switching amplifiers, you need to have a high input able to drive the transistor all the way from what? From the cutoff to the what? To the triode region. Are you following? To the triode region. The input should have what? Should have a high range, a large voltage that will drive the transistor from one, move the transistor from the off to the what? To the on. Different types. I think this is where we started and we ran out of time. Here. Let's see if you can help me here. This is called what? Class F amplifier. Class F power amplifiers. You have this one from last time. I just made a copy. You can tell that it's a Xerox copy. The difference between this one and the previous one is that this one here is actually not acting as a what? As a switch. Do you follow me or not? Not acting as a switch. Which means what? By the way, what does that tell you? It tells you that the input does not have to be what? Large to drive the transistor all the way from the what? From the cutoff to the what? To the triode. Clear? So that's a little bit better. Let's understand, first of all, how does this one work? Of course, this one, we already know that this is the RFC, this is the transistor, this is the input voltage. Notice, by the way, always missing in these types of diagrams, always missing is the biasing circuit. You need to have a biasing circuit to bias it in the right place. Okay, now what did we have here? We have a load here. We have a tank circuit, a parallel tank circuit, and then we do have a transmission line with a length which resemble what? Lambda over 4. I need to make a comment, first of all, on the length of the transmission line. When you say the length of the transmission line actually, is it changing length? Is it changing length? The physical length of the transmission line is the same. All what I'm saying is that it is resembling the effect of a what? Of a quarter of a wavelength, or a what? 1/2 of a wavelength, or what? 1 wavelength, and so on and so forth. The actual length, the physical length, is not going to change. In other words, are you going to move it up and back and back? It depends on whether the harmonics is even or odd? Of course not. Clear? So keep that in mind. So the length of the transmission line is resembles of a what? A lambda over 4, a quarter of a wavelength of a what? Of the fundamental frequency. This lambda is equal to what? C over what? C over F, where F is the fundamental frequency. And this is, of course, the blocking. Clear? What is the idea behind this? The idea behind this is to what? Is to allow this one here, this circuit is configured in such a way that it will keep the what? It will keep all the odd harmonics on this side. It does not allow the odd. See, in the harmonics, what is this one acting as? This one is acting as a short. It's supposed to what? What is supposed to? All the harmonics is supposed to go where? In here. Did you get this or not? You would like to what? Keep it there. Keep it there. In other words, don't let it go anywhere. Are you following me or not? Whereas the even harmonics, you would like it to go to the what? To the ground. Did you get this or not? Yes or no? Okay. Let's see, first of all, if you remember this equation, which is doubtful, but let's see if you remember this equation. Recall. What is Zn of a transmission line? Anybody? I don't expect you to remember. I don't expect you to. It's Z0 over ZL plus J Z0 tangent beta L divided by what? Z0 plus J ZL tangent beta L. At least do you recall such an equation? I don't expect you to memorize it, but do you recall it? Okay, so where beta is equal to what? 2 pi over what? Lambda, and hence beta L is equal to what? 2 pi over lambda times what? Times lambda over what? 4, which is what? Which is, help me, by pi 2. Now, if it is by pi 2, what is the tangent of by pi 2? Infinity. What is the tangent by pi 2? Infinity. Which means what? These are negligible. You agree? The J cancels with the J. And what do I end up with? I end up with the Zn equal to what? Z0 square over what? ZL. Do you agree? Now, if Z0, which is the characteristic impedance of the transmission line, the characteristic impedance of the transmission line, if it happens to be the same as what? ZL, which in this case is what? It's RL, then what do I have? I have Zn will be equal to what? ZL. Clear? Okay, what does that mean? What does it mean? When I say that the input is ZL, what does it mean? It means as if this one is what? It's not there. Which means what? The fundamental. Do I have a fundamental component here? I have a fundamental component here. Remember, the capacitor is acting as a what? As a short for AC. Did you get this or not? Cannot hear you. By the way, what is this acting as? At fundamental. At fundamental. It's acting as an open circuit. Did you get my point or not? Now, let's look at the what? The odd harmonics. The odd harmonics. What do I want Zn to be? What do I want Zn to be for the odd harmonics? I wanted to keep it here. Yes? So which means what? I like the Zn to be equal to what? Infinity. Yes or no? Now, in the odd harmonics, what is this behaving as? Short. You notice, by the way, when I say it's behaving short, you do realize that this is just an approximation. Do you understand or not? Just an approximation. If it is short in parallel with RL equal to what? Short. Yes? Which means what? It means ZL is equal to what? 0. Yes? Which means Zn equal to what? Infinity. Which means what? There's an open circuit here. So where does the harmonic go? Where the harmonic will remain here. So I have what? Third harmonic, fifth harmonic, and I have also the what? The fundamental. Add all of these harmonics. Add all of these, including the fundamental. So it's the fundamental, third harmonic, fifth harmonic. What does this one resemble now? It resembles a square wave. Did you follow me on that? But I did not need to what? To drive this transistor between the what? Between all of these, requiring a high voltage at the input to what? To go from the triode to the cutoff. Did you get my point? Okay. Now, how about the second harmonic? Let's understand the even harmonics. What do I want this one to be? I want this one to be a what? A short. Are you following me? Now, if I want it to be a short, what does it mean? It means that I would like this Remember, by the way, the input is a what? When I say a short, it means what? It means I want this to be equal to what? ZL. What is ZL? Well, the second harmonic. In the second harmonic, what is this? Second harmonic. This one is also acting as a zero, which means what? What is the overall ZL? Zero. I want the overall ZL here also equal to what? Zero. What should the tangent be? Beta L be? What is the beta L should be? The beta L, sorry, or even harmonics, beta L should be what? It should be N times what? Did I mess up? Did I mess up? It should be what? N pi. Are you following or not? Okay, but what is the beta? Beta is 2 pi over what? Lambda times L, which is equal to what? N pi. Yes? Pi cancels with this pi, which means length L is what? N over 2. Did you get this or not? It's a multiple of what? It's a multiple of lambda over 2 rather than what? Rather than what? Lambda over 4. Did you get this or not? One more time. Did the actual length of the transmission line change? The actual length of the transmission line did not change, but it is resembling a what? A half wavelength rather than a what? A quarter of a wavelength. Did you get this or not? Okay. So if it is short, if this is 0, by the way, what is this? 0, 0, Z naught cancel with the Z naught. What is Z in? ZL. But what is ZL? 0. ZL is not this one, because this one is also 0. So in other words, this implies what? Implies that Zn equal to what? ZL, which is equal to what? 0. Clear? Yes or no? Which means all the harmonics will go where? Will go, not all the harmonics, I'm sorry. All the even harmonics for the voltage will go where? Will go to 0. Clear? Clear? So what do I have? I have the following. I just explained this one here. What do I have? Let's see. Where did this come from? This is the VDS, which is the voltage in here. Is it a square wave? Where did it come from? It came from the what? The addition of what? The fundamental, third harmonic, fifth harmonic, seventh harmonic, and so on and so forth. All of them, and resemble what? Resembles this one. Clear? Is this one clear? Why is it 2 VDD? Why is it 2 VDD? It is 2 VDD because we do have a what? We do have a choke here. The maximum it can go is what? Is 2 VDD. Did you get my point or not? Okay, good. Now,
yeah. Is there going to be a DC component at the drain?
The DC component at the drain, yes. Otherwise, there is no power. We will calculate. Can you give me a minute? Can you give me a minute? Okay. By the way, remember the DC is coming from here. It's not coming from the load. It's coming from here. Clear? The AC, by the way, you either go what this way or you go what that way. But the DC, this one will block it. And this one, as far as the DC is concerned, is a what? It's a short circuit. The RFC, the choke, the RF choke. And because it's high and the omega equal to what? 0, you get what? This J omega L, yes? So at DC omega 0, DC will come here. Okay, but I need you, first of all, to explain this one to me. Why is this one like this? Why is the load like this? Now, notice, by the way, all the even harmonics will go where? The current. Remember, the even harmonics in here will be shifted to where? It will be shifted to 0. So the current, this current, which is the drain current, will be only the sum of what? The harmonics. Did you get my point or not? Yes or no? And what do you get when you add the harmonics to the fundamental? To the fundamental. Another fundamental, harmonic, second harmonic, fourth harmonic, sixth harmonic. I don't have the charts with me today, but I showed you the last time. You get something like this. Did you get my point or not? I don't have the charts with me. Do you remember which one I'm talking about? I showed you that when you add the even harmonics, you will get something like this. Clear? Okay. Now, what is this all about? Can you explain to me where is this? That is the voltage across the what? Across the load. Yes? Why is it a sinusoid? It's the even harmonics are going to ground, and the odd harmonics remain in here. Yes? So the only one that goes in there is what? is the fundamental, goes through the capacitor, which is this one. Clear? Now, let's calculate the powers. You see if you can help me here. What is the VL? Explain to me the VL. VL is the fundamental, or the peak voltage power. Peak voltage at the load. What peak voltage power? The peak voltage at the load. Explain to me, where did this come from? The 4 VDD over pi. Where did this come from? That's the what? That's the what? That is, in other words, when you expand this in a Fourier series, which component are you picking? That's this one, 4 VDD over pi. Which means, what is this? If you want to write an equation for this, it's 4 VDD over pi times what? Sine theta. Where theta is what? Omega naught t. Did you get this? Yes or no? Okay. What is IL? Which is the current, the fundamental current in the load. It's just simply what? This voltage. This voltage divided by what? By the resistance, which is what? By RL. Clear? No response. Clear? Okay. So what is the power delivered to the load? The R power delivered to the load is what? Is this times this divided by what? 2. Divide by 2 because this is what? This is a RMS you are calculating. Yes? So I get this. Did you get this? No response. Did you get this? Okay. Help me. How did I get this? Sorry, this one. The DC power. How do I get the DC power? I get the DC power. I need to get, first of all, the what? I need to get the what? The DC current. Yes? Okay. Now, let's see if you can help me here. This is the, excuse me, this is the current in the drain. Yes? What is the peak current? What is the peak current? This peak current. And why is it 2 times 4 VDD over what? Over pi RL. Notice, by the way, 4 VDD pi RL is what? Is this one. I mean, is this current? Yes? Why is it multiplied by 2? Why is it multiplied by 2? That's the peak. That's the peak current. I don't want you to confuse the word peak current with what? The fundamental current. Are they the same? They are not the same. Are they the same if the signal is a sinusoid? They are the same. If the signal is a single tone, then this is the peak current. It is the peak current. You agree? It is the fundamental. But if it is like this, where is the peak here? The peak is here. Where is the fundamental? The fundamental is halfway. Did you get this or not? How do you know that? You expand in a Fourier series, not this one, but this one. Did you get this or not? You expand in a Fourier series, this one. Is it, by the way, is this periodic? Of course it's periodic. I'm only sketching it what? During the time in which the transistor is conducting. Yes? Okay. By the way, is there an overlap? So you right away know that the efficiency will be what? The power dissipated equal to what? Will be equal to 0. The clear? Okay, good. Now, one more time. Where the 2 came from? Where is it? Here, sorry, this 2. Where is this? This is the peak drain current. What is this? This one. That's the fundamental current. If you multiply by 2, you get what? You get the DP, IDP. Yes? What is the DC? What is the DC? In a curve like this, in a waveform like this, it's IDP over what? Over pi. And the IDP is this one, the one that you just got it, and you divide it by what? You divide it by pi. So what do you get? 8 VDD pi squared times what? RL. Yes? That is what? What is this? That's the one that you were just asking. That's the DC current in the drain. Yes? What do you multiply it with? To get the DC power. You multiply it with the VDD, which is the power supply. Yes? So you multiply it with the power supply, you get what? 8. You get 8 VDD square over what? Pi square RL. Clear? Is this one the same as this one? Is it the same or not? Is it a shock? We already know from the diagram that you are not going to have any what? Any overlap between the drain current and the what? And the drain voltage. Clear? So we end up with what? We end up with an efficiency equal to what? Equal to this one, 100%. Yes? Now, do you remember this other parameter? Normalized power factor. How did we define it? Don't look. You are looking. You are cheating. Normalized power factor. How did we define it? We defined it as the R power divided by what? The V max, ID max. When I say V max means what? The maximum voltage across the what? At the drain. What is the maximum voltage at the drain? What is the maximum voltage at the drain? So VDD times what? Where is this? Can you tell me where is this? Where is this coming from? 8 VDD over pi RL. What is that? That's the peak current. Which is what? Which is this one? 1 second. No, sorry. Which is this one? I'm sorry. 8 VDD over what? Over pi RL. Clear? This one. What did we end up with? 0.159. Do you remember how much did we get for class A? Oh, it's written here, 0.125. Do you remember how much did we get for class D? It was like 0.3 something. You follow me or not? So which means what? It means it's better than this one. Are you following me or not? But the beauty of this one is that it is what? The input does not need to go through what? A high range. Did you get this or not? Okay. The problem with this one is that this transmission line is not easy to what? Integrate. Do you understand that or not? If you want a monolithic thing, everything is integrated. Can I replace it by this? Let's see if you can help. Can I replace it by this? What did I do here? What did I do? I put series tank circuits. Question, by the way. Does it have to be series tank circuits? Could they be parallel? Could they be parallel? Of course they could be parallel. I did just one example. Okay. What is this tuned to? 3 omega naught. What does that mean? At the 3 omega naught, what do I want this to behave? You are still not able to tell me. At the 3 omega naught, what do I want it to be? Open or short? But if it is short, then it means it will come here. I want to keep it here. I want the third harmonic to be kept here. You are losing me. Are you losing me or not? What is this in omega? This is tuned to 3 omega naught. Yes? At the 3 omega naught, what is this behaving? As an open circuit. Not open loop. Not open loop. Open circuit. What open loop? There's no loop. Open circuit. Why? Why? I want the third harmonic to remain here. Yes or no? Okay. What about a fifth harmonic? This fifth harmonic will go through. Do you understand why? Because it's tuned to 3 omega naught. Which means what? Do I need another circuit at 5 omega naught? So that I keep the 5 omega naught in here. Clear? But you might say, okay, Professor, am I going to use 3rd, 5th, 7th, 9th? What is the point that I'm trying to make? If you look at the what? If you look at the Fourier series coefficients, you will see that the higher the harmonic is, the level becomes what? Smaller and smaller and smaller, becomes a little bit what? Negligible. Which means what? You might not get 100% efficiency if you only put what? 3 omega naught. And they did that. They ended up with an efficiency which is decent. Which is what? Roughly between 85 to what? To 90. Is this a decent efficiency? By the way, still better than what? Class B. If you compare to Class B, which is the 78%. Are you following me or not? Yes or no? By including only what? The third harmonic. The more harmonic you add, the efficiency will get what? Close to what? 100%. Clear? But all of these are what? Are discrete components, so that you can what? You can integrate it within your board. Clear? No response. Clear? Okay. Now, there is one more before I move on. I need to move on. There is one class left, which is a class E power amplifier. Class E power amplifier. Now, there were 2 pages here. I lost the second page. I forgot it in my office, so I need to use the chart so that you can see it clear. Let me first of all explain it to you. This is class E. Again, this is a what? A switching amplifier, which means what? This is not the same idea as what? As a class F. The input needs to be what? Needs to be driven a little bit what? Higher. This one is trying to minimize the overlap between what? The voltage and the what? The current. Did you understand that or not? Remember, ideally, when we looked last time as a switching power amplifiers, ideally, there is no overlap. But if you do have what? If you do have some sinusoid, there will be some overlap. Clear? This one tried to what? Reduce that, as I will show you in just a second. What is the new thing that you see in this diagram that you did not see before? Yeah, you see this capacitor? This capacitor is external. Now, there is a parasitic capacitor in here between the drain and the source, but it will be in parallel with what? With the C1. In other words, what I'm trying to tell you is that in the previous configurations, the parasitic only resulted in what? Degradation in the performance. In here, no, it will improve the performance because you are using it as part of what? As part of the load network. This is part of the load network here. Clear? I will show you that in just a second. Clear? Okay. Now, this one, of course, is the what? Is the tank circuit. Are you following the series tank circuit here? It's tuned at what? At omega naught. Clear? Tuned at omega naught. And this is RF. Now, this is the switch. It's on and off. What is the goals? There are 3 goals in here. Listen to the goals, or 2 goals, sorry. Actually, 3 goals, 2, I grouped it together here. I want the drain voltage, which is Vx. When the transistor is what? When the transistor is on, what should the voltage here be? When the transistor is on, when the switch is on, which means what? This is closed. What is the switch? What is the switch? What is the voltage here should be? 0. I would like the voltage here to drop to 0 before the switch goes what? On. Did you understand that or not? I would like the voltage to go what? To 0 before the switch goes on. And I also want the slope of the voltage. With the voltage when it goes down, I want the slope of the voltage. Slope of the voltage means what? dVx by what? dt with time. I want it also to be equal to what? 0. I want to show you the diagram first so that before I explain to you the operation. I want you to see this. This is the voltage. And this is the current. The dotted is the current. This one is the voltage. Do you see at this point here? At this point, the voltage, in other words, where is the on? This is the on. You agree? I would like the what? I would like the voltage to reach what? To reach 0 before the switch goes what? On. And I want the slope. In other words, I want this one to be like this, such that the slope here equal to what? Equal to 0. Did you get my point or not? Yes or no? What is this, by the way? What is this? This is the on. I wanted in the on, during the what? During the turn off. I want the volt. See this one? The current is what? Is dropping. Because it's getting into the what? The off period. I wanted during that time, I want the voltage to be what? Small. During that time. I want the voltage to be what? Small. Why? So that the power dissipation here becomes what? It's very little. Did you get this or not? Okay. How do they design this? They design this such that this circuit, do you see this circuit? Present what is known as a critically damped circuit. Do you remember the critically damped? Did you take any courses in control? There is overdamped, underdamped, undamped, critically damped. Do you remember it or you don't forget about it? You totally forgot about it. What does undamped means? When we say this circuit is undamped, what does it mean? It keep what? Oscillating. No, it keep oscillating. Undamped. Undamped. When we say what? When we say underdamped, what does it mean? At the beginning, I cannot believe I'm spending time on this. You should have had it before. Underdamped means what? Means you start what? Oscillating, but the oscillation will what? Will die down, with time. Clear? Okay. Overdamped means what? There won't be any what? There won't be, no, overdamped will not be oscillation. Are you following me or not? Critically damped is the one that what? That the decay will be what? The fastest. The decay to what? To zero. Did you get this or not? That's what we want in here. We want this one to decay to what? To zero very quickly, and the slope to be what? To be zero. Do you remember what is the C for the critical? No? Do you remember this? What is the order of this network? Second order. Yes or no? Do you remember what is the frequency response of a second order? Or transfer function of a second order system? No? Not ringing a bell at all? It's h of s equal to what? You remember? What is omega n? Omega n is what? Is the natural frequency. Natural frequency means what? Means undamped. Undamped. It's not damped. This is the natural frequency when there is no damping. What is the C? Damping factor. I don't want to get into this because there is no point if you don't have the background. And what is for a critically damped? For a critically damped. Anybody? C is equal to what? 1. Clear? Underdamped, the C is what? Less than 1. Overdamped, the C is what? Greater than 1. Undamped, the C is equal to what? 0. Notice, by the way, if C is equal to 0, what are the poles? At S equal to what? Plus or minus J omega n, which means where are they located? They are located on the J omega axis, which means what does the output look like? A sine or a cosine? Sinusoidal. Yes or no? If C is greater than 1, what do you see? You will see that all the poles are what? Are on the real line. Are you following me or not? Which means what? There is no what? There is no oscillation. Yes or no? Cannot hear you. Okay. If C is less than 1, you will see what? You will see that the poles will have a what? A real part and a what? Imaginary part. On the left-hand side of the S-plane. Yes? The real part will result in what? The damping. The imaginary part will result in what? Some fluctuations. But with the damping, the fluctuations will what? Will die down. Let me show it to you quickly. Let's assume you apply a step function. Underdamped, what does it look like? Underdamped, what the output look like? The output would look like what? This. Yes or no? Heavy damping will die down. Yes? Undamped, what does it look like? Undamped. I go there and then what? Oscillate, oscillate. Yes? Critically damped, what does it mean? This one will go what? There here. It's not going to what? Oscillate. It's going to what? Approach this very quickly. Did you get my point or not? Yes or no? Okay, I cannot explain this. This is EE. I even forgot what the number is. 480, which is control stuff. And that's why I don't want to spend time on the class E. But did you get the idea? Okay, you have to remember one thing here, is that if the voltage, listen to me, this is the point that I'm trying to make. You know the capacitor cannot change its voltage instantaneously. Do we agree? If the voltage at the input is low, by low I mean what? Below the threshold. This one is supposed to be what? Cut off. This voltage is supposed to what? Rise high. Yes or no? But this one will not allow it to what? To change very quickly. Why? Because there is a voltage on the capacitor and the capacitor cannot change its voltage instantaneously. It takes time, and that explains this in these diagrams here. Are you following me or not? And the same thing with the what? When the input is what? when the input is high. See, when the input is high, what is this supposed to be? If the input is high, above the threshold, what is this supposed to be? On. This voltage is supposed to go to what? 0. This one will prevent it from going to what? To 0 very quickly. Do you understand that or not? Yes or no? Okay. Now, read this one. I mean, try to understand it and let me know if you do have any questions. The analysis of this one is a little bit more involved. Clear? And the voltage, by the way, the voltage at this point, see, in the previous configurations, what was the maximum voltage in here? 2 VDD. In this, it might go to what? 3.5 or 3.6 VDD. Why? Because there is a capacitor in there. Did you get my point or not? Is that better or worse? When you do have 3.6 VDD here. But you need to look at it from different point of view, which is the following. Is that if you are going to use the new technology, new sizes for what? For your transistors, those small sizes, you are not going to be, this one cannot handle the 3.6 voltage in here. Actually, even the 2 VDD is what? Relatively high. Did you understand what I just said or not? There might be what? There might be a breakout in the transistor itself. Clear? No response. Clear? Okay, good. Now, the rest I need, it's not in the charts, but I want just to survey the power. What did we, let's summarize this. In the switching power amplifiers, the efficiency was what? High. You agree? But the linearity was what? Not so good. Are you following? The linearity is not so good. The power mode, the current mode, the constant current mode power amplifier is the other way around. The linearity is pretty good, especially if it is class A, but the efficiency is what? Is not so good. The question is, can we improve it? With some techniques, can we improve, for example, the linearity, or can we improve the efficiency, or can we improve both? So in general, the performance. I'm not going to go into details into circuits. I just want to show you the methods that might be used. Did you get my point or not? So that you get an idea. Again, don't write anything. Just listen to me, and then you can download it from the site. Okay, we need to apply some kind of control. The control is either applied at the input or at the output, or even the control can be applied at the power supply. At the power supply, where the drain is connected to. Did you get this or not? Again, what is the purpose of this? Trying to prove what? The linearity of your transistor. Let's start with the simplest one of them all, which is the what? The back off. We already know that. Let's understand, see if you can help me. What is the back off here? That's the amplifier. Is it non-linear? At this point, what did we reach? Is the 1 dB compression point. Yes? What do I want it to be linear. So I need to what? I need to back off all the way to this point. From here to here, this is the back off. We call it the back off. And the back off could be anywhere between what? 5 to what? 10 dB. Or even a little bit more. Is that a large value? That's a relatively large value. Just to avoid what? You do understand why am I trying to avoid operating here? I'm trying to avoid operating here to reduce the what? To reduce the distortion due to the nonlinearity. Now, if the modulation happens to be constant envelope, then it's okay. Do you follow me on that? Why? Because those spectral regrowth will be what? Minimal. But if not, then it is a problem. Clear? Who will suffer? When I move this one to here, what will suffer? The power added efficiency. Let's see if you still remember. What is the power added efficiency? The power added efficiency is what? Is the drain efficiency times 1 minus the what? The gain. Oh, sorry, 1 over the gain. Yes? Will the gain be lowered? The gain will be lowered in here when you come what? When you come in here. So this term will be what? Will be lower. Did you follow me or not? Okay, that's the price you pay. The other type is a funny one. I admit it's a funny one, but I want you to understand what is the other one. Pre-distortion. What do you mean? By purpose, you pre-distort your signal before you what? Amplify it. Are you following me so far or not? How? How do you pre-distort it? By generating nonlinearity, which is opposite to the nonlinearity generated by who? By the PA. So that when you, remember, when you connect two systems in series, the overall frequency response will be what? The product of the frequency response of the first one times the second one. So if they have what? If they have distortion in opposite direction, in other words, one of them is like this, the other one is like this, when you multiply them together, you will end up with something which is what? Which is constant. Did you get my point or not? Yes or no? Okay. Now, I want you to understand one thing here. In this diagram, in this block diagram, when did I do the pre-distortion? I did the pre-distortion at the baseband, which means what? Before the modulation. I could have done it after the modulation, but it's much better to do it before the modulation. Why? Because before the modulation means what? Means you are dealing with baseband. You can use what? Digital circuitry. Clear? No response. Clear? This is called what? Pre-distortion. Pre-distortion is also used in communications over what? Over wireless channels. You will take this in 535 when you use what is known as what? Equalization. Equalization. You are trying to what? You are trying to model the channel characteristic, and you try to what? Equalize it. Equalize it means what? Means when it is what? When it's showing some dips, you need to show some what? Gain. So that when you group them together, they will what? They will end up with a what? With a flat response. Clear? Clear? But we don't talk about equalization in this course. I had too many things to cover. But did he discuss it or not yet? You are looking at each other, which means what? You have no idea what's going on?
I think it's next topic.
Oh, so, but he will discuss it. I think in 535, not 635. He will discuss the equalization thing, especially, by the way, for GSM. For CDM and top receiver, sometimes they use what is known as the rake receiver. Did he talk about the rake receiver? He did or not? Huh? Coming attraction. It's coming attraction, coming attraction. Okay. Now, let's look at feedback technique. Now, you understand what feedback means? Means from the input, I'm taking it back to the what? To the, did I say from the input? I'm sorry. From the output, I'm taking it back to the what? To the input and adjust it. Clear? When you do have control systems, feedback systems, the linearity will improve. However, the danger is that the system might become what? Unstable. Are you following? Whenever you do have a feedback loop, we will get to that when we talk about the phase lock loop later in the semester. Whenever you do have a loop, you need to worry about what? Adjusting the loop gain properly, putting what? Proper delays, compensating for the delays. Otherwise, the loop might become what? Unstable. Clear? But let's understand, first of all, the difference type. One technique they call to what? The Cartesian feedback. Cartesian means what? The IQ feedback. Let's see if you can help me here. Forget about the feedback for a minute. And what is this, by the way? These are op-amps. You follow me on that? Operated as a what? What is this? When I put plus and I put minus, this is a what? A difference op-amp. A difference op-amp means what? The output is proportional to the difference between the two. Don't worry about this right now. Don't worry about the op-amp. This is the I, and this is the Q channel. One is multiplied by what? Cosine omega naught t. The other one is multiplied by what? Sine omega naught t. That's the quadrature modulation. It gets added and amplified. I'm going to take the output from the power amplifier, and I what? Demodulate it. In other words, down convert it. So I do this down conversion. However, I introduce a phase shift between this one and what? This one, to take into account or to compensate for what? For the delay. Are you following me on that? For the delay, you need to compensate for that. And that data will help you establish stability in your what? In your feedback loop. So I demodulated, yes? And then what? I filtered it out. Yes or no? Okay, by the way, once you filtered it out means what? Means that it, by the way, this I'm assuming the I and Q was already what? Shaped, waveform shaped. This one is the same thing, and you compare it with the input and you try to see what? Compensate for the what? For the difference between them. Clear? Clear? This is called what? This is called the Cartesian. You understand what they call Cartesian? Cartesian means what? Means the I and the what? Q. Let's see if you can help me with the next one. Polar feedback. What is polar feedback? In a polar feedback, how do you represent a complex number? In a polar. In a Cartesian, you are represented by what? I and the Q. In a polar, you represent the magnitude and you represent the what? Phase. In here, you use two loops. One for the amplitude to compensate for distortion in the amplitude, and the other one to compensate for the phase. Compensate for the phase, that is your regular phase lock loop. Did you understand what I just said? No. So what you have here is what? Is a reference phase, and the output of the power amplifier will be fed back. This is a phase detector. This is what is known as a what? A loop detector. Loop detector. This is a loop filter. Yes? What is this, by the way? This is the error in the phases. The error in the phases between the ideal and the what? And the output of the power amplifier. Clear? What do I have here? Do I have, by the way, if the phase detector is 0, what does it mean? The output of the filter is what? 0, which means the VC, what is VCO stands for? Voltage controlled oscillator. A voltage we'll talk about this in detail shortly. The VCO is a device in which the output frequency is controlled by an input voltage. Yes? Is it slowly changing? The input here, is it slowly changing? In other words, does it look like almost a DC? Almost a DC. Why? Because this is a low-pass filter. This is a small changing thing. He will change the what? He will change the frequency. The frequency of who? When I say VCO, what is this frequency? That is the carrier frequency. Did you get my point or not? Yes or no? Okay. Now remember, we are dealing with what? Two types of modulation. Amplitude modulation and what? Phase modulation. Did you get my point or not? This one is tracking the what? The disturbances or distortion in the phase modulation. Okay, then you apply it to a VGA. What is the VGA stands for? A voltage gain, sorry, variable gain amplifier. Variable gain amplifier. The output of the PA goes into a what? An envelope detector, which is detecting the what? The envelope, which is what? The amplitude modulation. Did you get this or not? It goes again with what? With a reference. You are comparing it with the reference. The error get filtered out, and the output will control the gain of what? Of this variable gain amplifier. Clear? Clear? This is referred to, by the way, which loop is faster? This one or this one? Which loop is faster? This one is faster. Why? Because this one is what? The modulation is on the what? The modulation, this one is an envelope. The envelope is a what? Slowly changing. Whereas this one is faster. So you need to compensate for those speeds. Otherwise, you are not going to what? You are not going to put back the envelope. I mean, you adjust the envelope properly on the what? On the phase modulated carrier. Clear? Clear? Okay, good. Now, let me show you another one. Feed forward. This is also funny. Let's see. Feed forward means what? No feedback. Is that good for stability? And that's good for stability. A feed forward, I don't worry about what? Stability. Clear? Okay, let's see if you can help me here. This is the input voltage. This is the RF. Yes? I take it to the amplifier. That's the power amplifier. That's the main power amplifier. Now let's assume the gain is what? GB. The output is the what? Has some distortion in it. So the output has some distortion in it. I called it M. What is VM? Give me the equation of VM. VM is equal to what? GB. This is a voltage gain, by the way, not the power gain. Voltage gain. VM equal to GB times what? VI, the input voltage, plus some what? Plus some distortion. Did you get this or not? Oh, I'm going to take it here. Forget about this for a minute. I'm going to take it here, and I'm going to apply it to an amplifier with an inverse gain. So the gain in here is what? GB. The inverse of this guy is what? 1 over GB. Yes? What do I get? What is VN? What is VN? VN is 1 over GB times this. So it's 1 over GB times this. So what do I get? VN plus what? BD over what? GB. Did you get this equation? Yes or no? Okay, good. Now, what am I doing? I am subtracting the VN here. Yes? So what am I getting here? When you subtract the VN, you get VD over GB. Amplify it with the GB, you get what? VD. In other words, the VQ is the what? Is the VD. Yes? and you subtract it from who? From this. You remember, what is this? This is GBVN, which is what I want for linearity. For linearity, I get rid of the distortion. Clear? Clear? No response. Clear? Okay, what is the problem? Do you see a problem? Say that again. How to control the gain? It's very hard to control the gain. By the way, this is 1 over GB. In addition, is there a delay between this one and this one? All of these delays in this branch and in this branch needs to be what? Compensated for. Did you get this or not? This equation is very nice on a piece of paper. Did you understand what I just said or not? On a piece of paper, these equations are what? It looks very nice. But in reality, there is you need to introduce a delay compensator here and a delay compensator here. Because going from here to here, there will be what? Some delay as compared to this one. So you are not subtracting. In other words, this, which is the Vn, will not cancel this one because it's coming at a what? At a later time. You need to compensate the delay to make sure that they cancel each other. Clear? No response. Clear? Okay, good. That's a Pete form. The good thing about it is, by the way, what is another not so good about it? You are adding too many components. Are you following that? Which means what? Power requirement will also what? Will also increase. Clear? Okay. How about this one? Let's see if you can help me. This is called what? Linear amplification with nonlinear components. You are performing linear amplification, but using what? Nonlinear components. How could that be done? Let's see. Do you recognize this equation? What is this? Vn of t. Remember, what did we say? We said that if the input is a what? Is a constant envelope, then I don't have any problem. You follow me or not? I don't have any problem with distortion. Clear? Okay. But if the input is of a variable envelope, which means what? There is an envelope variation, then we do have a problem with distortion. Vn, what do I have? I have both an AM modulation and a what? Phase modulation. I can write this in two ways. I can separate them into the following. 1/2 V0 sine omega naught t plus Vt plus what? Theta of t minus 1/2 V0 sine omega naught t plus Vt minus theta t. Clear? What do you recognize in these two components? Do they have a variable envelope or a constant envelope? Say that again. The constant envelope. The variation in the amplitude was translated to a what? To phase variation, such that sine of theta t, the sine of theta t is equal to what? 80 over this V0 constant. Did you get this or not? Yes or no? So what do? We take the signal, we take the input signal, and we separate them. One to this, and one to this term. Did you get this or not? Using what? These are nonlinear. PM, what does PM means? PM, phase modulation, is performed here. Why? This one here, this is phase modulation. Did you get this or not? I separate this term here. I separate this term here. I amplify them separately. By the way, do I have a problem in amplifying them separately? Why? Because neither one of them have a what? Both of them have a what? Constant envelope. So I amplify them separately, and then I add them to go to the other. Clear? But the problem with this one is the design of this guy. This design of this guy is not easy. But did you understand the basic concept? The basic concept is any signal which has both AM and what? Angle modulation can be separated into what? Into two types of signal, or two parts of the signal where only angle modulation is there. No more amplitude modulation. Amplitude modulation is constant. Clear? Oh, and the final, I did take too long this one. The final one is what is known as what? Envelope elimination and restoration. Let's understand what this is all about. Same idea, by the way, same idea. What is coming in here?
The time is 18
What is coming
o'clock.
in here? What is coming in here is this guy. A of t cosine omega naught t plus what? Phi of t. I pass it through a what? A limiter. By the way, is this a linear device or a non-linear device? A limiter. You have to look at the space to get the answer from the space. Limiter. Is it linear or is it non-linear? What? But of course it's not linear. What is the characteristic look like? Limiter. How do you? Yes or no? As you are limiting yourself, you are clipping. So any variations, any amplitude variations. By the way, is it possible that we don't have AM modulation? It is possible, but the amplitude, because the signal has been propagating, are you following me or not? It might be received with what? With the fluctuations. Clear? But here we are talking about at the transmitter side. So we are putting what? AM modulation. If you see, for example, if you look at an FMD modulator, you will see a limiter at the receiver. Why? Why do we need a limiter at the receiver in an FMD modulator? Because when the signal propagates, the amplitude is no longer going to be what? Constant. You would like to what? You would like to cut all of these clippings at the what? At the beginning, before you go into what? The demodulation. Clear? Oh, so let's review it one more time. Limiter. Once it goes limiter, it means what? You have killed the what? A of t. Did you understand what I just said? You have killed A of t. A of t became what? Constant. But the information, there is information in A of t. So what do? You apply the signal to a what? An envelope detector. An envelope detector does not care about the what? The angle. Do you agree? Yes or no? Does not care about the angle. It's just detecting the envelope. So when you detect the envelope, let's call it A of t here, you amplify it, some amplification here, and then what are you controlling? Where is this one going to go to? Look at it. This one, by the way, here, what is this type here? This is a constant envelope, FM modulated. You follow me or not? It's going to go to the what? To the power amplifier, like normal. But where is this one headed to? Where is this one going to? This one is going to the power supply. In other words, this one is acting as a what? As a drain modulated power supply. I'm not sure that you followed me here or not. This one is replacing who? What is it replacing? VDD. It is replacing VDD. This point here is going to come here. Of course, amplified certain amplification, and you go into the what? Into the RFC. And then this is the what? This is the matching network and the RL and so on. Clear? This is what is known as envelope elimination. Where did the elimination came? Elimination is here. And what? Restoration. You are restoring it. Clear? Clear? Oh, now these, again, as I told you, we did not get into the details in this. We just simply don't have the time. The power amplifier is a course by itself. Are you following me or not? It's a course by itself. How many of you took 448? None of you took 448? Did you do any experiments with power amplifier? Power amplifier usually is not discussed in any courses. You follow me or not? Too much problem. But I think you got a little bit of an idea. Did you get an idea? No response. Did you get an idea? Okay, good. Now, let's get into the beast. That's the beast. Which is the what? This, by the way, will be the topic of your second project. Aaron will write it down and he will be posting it probably within a week or 10 days or something like that. Clear? And by the way, it is recommended that you work with the same partner that you are working with in this in the systems project, in the MATLAB project. Clear? Unless, if, of course, if you don't like your partner, you can always get divorced. Okay. Low noise amplifier. Where are we right now? Are we in the transmitter anymore or no more? No more. We have reached the what? Receiver. Again, notice, in the transmitter, the reason that we only looked at a power amplifier. Why? Because the oscillators, the mixers, we are going to be talking about them anyway in the case of what? In the receiver. And the challenges in the receiver is much higher than the challenges at what? At the transmitter. Because at the receiver is where the what? The degradation in the power, the interference, the distortion, and so on and so forth, are the intermodulation components, and so on and so forth. Clear? Okay. So the low noise amplifier. Let's first of all understand the basic issues. What are the basic issues? Let's start first of all with the noise figure. What do I want the noise figure to be? I want the noise figure to be what? Relatively low. Why? When we discussed the noise figure, we saw that the noise figure of the first component of our receiver chain is the one. Do you remember the equation? What is the equation? F total equal to what? F ln A plus F rest minus 1 over what? G ln A. Do you remember this equation? Do you answer what you mean by F the rest? I grouped all the rest together with one block. This is F the rest. Did you get this or not? So what do I want? I want the noise figure to be low. Why? What does the noise figure affect at my receiver design? The sensitivity. The noise figure affects the what? The sensitivity of your receiver. In other words, what is the minimum detectable signal that can be sensed by your receiver? Are you following me or not? Yes or no? The whole thing, the material that we discussed earlier in the semester has been deleted from your brain. Is that true or false? By the way, did I mention that the final exam is comprehensive? It's comprehensive. So you better what? You better don't forget anything. What do I want the gain of the low noise amplifier to be? I would like it to be high so that the effect of the noise in subsequent stages becomes what? Negligible. However, I don't want it to make it too high. Why? Because if you make it too high, and if there is happening near that receiver, strong blockers will go through the what? Through the low noise amplifier. If it is a high gain, it will result in what? It will result in blocking your entire receiver. Do you understand what blocking the entire receiver means? Means the sensitivity will approach what? 0. You are not going to be sensing the what? You are not going to be sensing the what? The signal. And the amplifier actually will begin to what? Will begin to go down. Are you following me or not? Which means what? It's going to provide attenuation in. Clear? In addition, let me show you one thing so that you understand what I'm talking about. Let's assume that I do have a what? A full frequency division duplexing. You remember the frequency division duplexing? Okay. So what do I have? I have this is my power amplifier, the transmitter. Okay. And then I take it to a what? A duplexer. Okay. And this is the receiving chain. This is the LNA. Clear? Actually, at the beginning, we do have the what? The frequency, the band select, which is, let's assume that it's part of the duplexer. Okay. Now, let's assume, just an example. Let's assume this one is generating 30 dBm power. 30 dBm means how many watts? 1 watt. Are you following me? And there are a lot of systems that require this. For example, GSM or the CDMA require the 30 dBm. Now, the duplexer is supposed to do what? The duplexer is supposed to provide isolation from this port to this port. This one is supposed to go to where? To the antenna and radiate it outside. Yes or no? But let's assume, just for the sake of argument, there is what? Isolation of, let's say, minus 50 dB. Relatively decent. Do you agree? Do you answer what minus 50 dB means? Means if this one is generating at 30 dBm, what would the power be here? The power in here will be minus 20 dBm. Now, where is this one going to go? Let's assume that it's going to go to the what? To the mixer. If the gain of this guy, is high, what will happen? This signal, by the way, which one is stronger? This signal or the received signal? Received signal means what? Means from outside. The received signal is almost dead. Are you following me or not? This one is going to be stronger. And if you do have what? If this one is providing gain, let's assume this one provides gain for 20 dB. 20 dB. What is the power here? 0 dBm. You follow me or not? And this 0 dBm might result in what? Might result in driving this into what? Into compression. And when you go into compression, what does it mean? It means that you will generate the third order intermodulation, all of these distortion components that we talked about it earlier. Clear? So you need to be careful with designing the gain of your amplifier. You have an idea about what your overall gain of your receiver should be. Excuse me. And instead of concentrating it in one block, try to what? Distribute it over what? Over multiple stages of your receiver. Clear? Oh, good. So, now, gain over the band of interest. What does that mean? What does that mean? When I say the gain over the band of interest, what does it mean? You have to understand that this low noise amplifier is going to pass the entire band of interest. Why? Because the channel select is going to be where? Somewhere after, in the IF. Are you following me or not? No response. Yes? By the way, regardless of whether your receiver is a heterodyne receiver or a what? A homodyne receiver. You still need to what? To pass the entire band. Did you get this or not? So you need to make sure that what? That your band is, so the gain is almost what? Constant over your band of interest. Clear? How about linearity? What will this one affect? By the way, how do I measure the linearity? I measure it either from the what? IP3, or I measure it, do you remember what SFDR stands for? The spurious free dynamic range of your amplifier, and so on and so on. What does it affect? The linearity. Does it affect the sensitivity, or does it affect the distortion stuff? It will have an effect on what? On the distortion stuff. Clear? The noise affects the what? Sensitivity. This one affects selectivity. Input and output impedance matching. Where is this one going to go? This is the antenna. Yes? This one, the input needs to be matched to what? To a 50 ohm, for example, wire. Are you following on that cable? Small cable needs to be matched. Clear? Now, we will see shortly, probably next time, not probably, definitely next time. We will see next time is that it is a challenge to try to achieve maximum power transfer at the same time as what? Optimizing or minimizing the noise figure. Do you understand that or not? See, in order to get matching maximum power transfer, we already know the equation. The equation being what? The equation being that the impedance, the input impedance or the load impedance needs to be the complex conjugate of the source. Yes? We don't know what the source impedance is. Are you following me? That source impedance that results in a maximum power transfer might not be the one that results in what? In minimum what? Noise figure. Do you understand that or not? We need to what? We need to balance these things to achieve optimization of the noise figure, and at the same time trying to what? Maximizing the power what? Power transfer through the use of matching circuits. Of course, we also need to deal with, and we will see that when we get there, whether the low noise amplifier is going to support a narrow band or whether it's going to support a what? A wide band. And also we deal with what? Stability. Stability, by the way, in all issues, in all circuits, you need to worry about what? Whether your system is stable or not. And of course, also the what? The power. Consumption. The power consumption. Again, we want to minimize the power consumption in it. Clear so far? Okay, good. Now, so the LNA requirement, again, introduce low noise to provide for high sensitivity. It provides a gain roughly between 10 to 20 dB to amplify the received signal power without adding too much what? Too much noise. Keep that in mind. When you are amplifying the signal, you are also amplifying the what? The noise. You don't want what? You don't want the device to introduce what? Noise of its own, a large sum. You always remember, signal to noise ratio, as you move down, it's going to go what? Down, degrade. Clear? Clear? No response. Provide gain, 10 to 20 dB to amplify the received signal, linear characteristic in the presence of large undesired signals or blockers. Input matching, 50 ohm to provide maximum power gain. We already talked about this. If the LNA, by the way, is preceded by filters These filters require 50 ohm loading for a proper what? For a proper operation. If they are connected to the antenna directly, we still need a what? 50 ohm to match the characteristic impedance of the what? Of the cable. Clear? Of the feeder cable. Clear? Okay. Now, the effect of, we already talked about this, the effect of the LNA is what? Is the NF LNA. All of these, by the way, are not in dB. So this one actually should be what? Should be F, not NF. Did you get my point? Okay, should be F, the noise factor. What is this, by the way? Do you remember this equation? This is how to calculate the what? The overall what? The overall IIP3. Clear? The effect of the gain on the overall IIP3. You notice, by the way, its effect is not as severe as what? Is not as important as what? As far as the NF is concerned, because this one is raised to the what? To the -1 here. IIP3 of LNA reduces the in-band. What does that mean? High IIP3 reduces the in-band IM distortion. Why? IIP3, high IIP3 means what? Means the amplifier is what? It's more linear. Yes? And why am I only interested in the in-band IM modulation, distortion? In-band. And out-of-band, what do I care about? The filters will get rid of it. Clear? Okay. Total IIP3 is decided by what? The mixer and the subsequent blocks, not by the what? The LNA performance. You can see that its effect is what? Is minimal, because this one is 1 over this. Clear? But for this one, it is important. Now, if zero IF receiver is used, why is IIP2 also important? What is IIP2 stands for? Second order intermodulation product. Yes? Which is what? Which is when the second order intermod. What is the second order intermod? Omega 1 minus what? Omega 2 or omega 1 plus omega 2. Omega 1 plus omega 2 I don't care about. Why? It's going to be filtered. But omega 1 minus omega 2, and help me, omega 2 minus omega 1 becomes crucial in a what? In a zero IF. Because the difference between them, especially if they happen to be what? Close to each other, the difference between them will fall into the baseband. Did you get this or not? So by the way, we talked about this all earlier in the semester. Unfortunately, some of you might have forgotten it, but we talked about them in detail. Okay, now let's look at the noise. Try to understand the noise before we continue next time with the analysis of the noise. Where are the sources of the noise? Where are the sources of the noise? Where are they coming from? We have what is known as what? The drain current noise, and we do have the what? The gate current noise. Now, most of the time, we will see that the gate current noise, we are going to what? Ignore it. Are you following me or not? We ignore it. However, I need to understand one thing here, is that these two noises are not totally uncorrelated. They are not totally uncorrelated. Some of them are generated from same phenomena, which means what? There is some correlation between what? Between them. Did you get my point or not? Yes or no? Okay. Now, but before we get into this, let me show you first of all, again, don't write anything, just follow me here. I want you to understand how we are going to represent the noise sources. We'll get to all of these equations next time. Let's say, concentrate. I have a noisy network, a two-port network. Two-port means what? An amplifier is a two-port. A mixer is a what? It's a three-port network. The amplifier is a two-port network. That's the input, that's the output. This is a noisy network. I can change this noisy network in a what? Noiseless network by representing or by modeling the noise sources as a what? As a voltage and as a what? As a current. This is a voltage noise source. This is a what? A current noise source. Did you get my point? Okay. What is this notation? Vn square bar. What is that? That's the mean square. Why? Because the noise is a random process. I cannot write an equation for the noise. Have you seen noise? In a lab or something. Have you seen noise? Noise is all over the place. Are you following me or not? You cannot write an equation. You need to deal with it in a statistical fashion. So I have what? Vn square bar, that's the mean square. What is this measure of? The mean square. What are you going to use? This is the average noise power. The average noise power. From which source? From this source. This is the what? This is the average noise power from this current source. Clear?
Professor.
Clear? Okay, good. Now,
Professor, we have about 5 minutes left. Just a heads up.
okay. We just started. Time goes very quickly. Okay. Now, how do I find these? How do I find these? By the way, we will relate them to our low noise amplifier next time. This is in general. This is general analysis. Clear? For a two-port network. How do I find the Vn square bar? I short circuit the input what? The input ports. I short circuit the input port and I measure the output noise power. Did you understand what I just said or not? What happens when you short circuit this? When you short circuit this, what happens? This one has no what? Has no effect on the node, on the network. Do you agree with me or not? Which means what is the source that will affect the noise output? It's Vn. Are you following me now? And if you know the gain of this guy by measuring the output noise and the output, you will be able to figure out what is this one. Did you get my point or not? Okay. How do I find this? I leave it open. When this one is leaving open, the current will all go what? Into the network, whereas this one does not play at all. Did you get my point or not? So in this case, to find In square, you open circuit the input ports and you measure the noise power and the output. Clear? Now, assume that the two noise sources are what? Uncorrelated. They are uncorrelated. Notice, by the way, if they are uncorrelated and if we are assuming they are Gaussian distributed, then they are what? They are independent. Remember, uncorrelated random variables does not necessarily means they are what? Independent. But if they are what? If they are jointly Gaussian, if the two random variables are jointly Gaussian and uncorrelated, then they are what? They are independent. So, assume that the noise sources are what? Are uncorrelated. And since Gaussian, they are what? They are independent. How do you write it? Let's see if you can tell me. How do I represent this? This is a noise source. I can represent it by a what? A resistor, which is the what? This, by the way, this is the source. I care about this one. I don't care about this one. Why? Because this is the signal source. I'm dealing right now with the noise. What is this? Can you tell me what is this? This is the noise generated, the noise power generated by the source resistor, by the source resistor, by the generator resistor. And it is in series with what? RS. And RS is what? Noiseless, because you already took it into account. Do you still remember what is this equal to? No. 4KTBR. You still remember? Okay. Can you review this in the weekend so that next week we go a little bit smoother? Because your memory looks to me like a little bit on vacation. So review it a little bit. Okay. This is Vn, this is In. This is the Rn that you are looking for. Now, what am I interested in? I'm interested in measuring the noise power at what? At the output. Due to what? Due to all of these sources. Can I apply superposition? I can apply superposition. If you want to take the effect of this guy, what do you do to this guy? Short circuit. What do you do to this guy? Open circuit. You find the effect of this one, which I'll show you shortly. Yes? How about this one? The effect of this one. Short circuit this. Open circuit this. Yes? How about the effect of this one? Say that again. Why open? Short. Short circuit, short circuit. You don't want this in there. So it's just the current. The current will go in here. Are you following me or not? Because you need to take into account the RS. Are you following me or not? Okay, the RS is there. This is not the same as what we were talking about here. What we were talking about here was nothing there. And here there is an RS. Where is the RS going to go? Did you get this or not? Okay, good. So, the goal, what is our goal? Our goal is to try to minimize the noise figure. Yes? Okay. What is the noise power and the output has how many contributors? 3 contributors. Which is what? Which is this one, which is due to the source resistance, which is this one, due to this source, and which is this one, due to this current source. Did you get this or not? Okay, good. Can you tell me where is this equation came from? What is it?
Professor?
N0 square bar. What is this? That's the mean square value of the noise power at the output. Total. Consisting of how many components? 3 components. Question. Why am I adding? Because I assumed that this and this are what? Uncorrelated. And they are definitely independent of who? Of the source. The source coming from somewhere else. Did you get this or not? All of these, this one and this one, are generated what? Internally, from the device itself. This one is coming from different place. Yes? No response. Yes? Okay, good. Now,
Professor?
what is this? Explain this one to me quickly.
Professor? For sure.
VRS, what did I do to this? Short, open. What is it? VRS square, Rn, it's behaving as a what? As a voltage division. Rn divided by what? Rn plus Rs, the whole thing what? Square. Why is it times AV square? Because I'm dealing with what? With power. Did you get this or not? Yes or no? Okay, don't say anything.
Professor, we're about out of time. Yeah, sorry about that.
Okay, we'll continue next time. Clear? Okay. By the way, you do have something due today, so don't forget to submit.
And this concludes EE 544 on Thursday, April 3rd, 2014.